Okay, in this video, we're going to take a look at hypothesis testing for a single sample mean. In our last section, we took a look at some introduction exercises to hypothesis testing, and now we're going to look at how hypothesis testing for a sample, or for at least a population mean, a single population mean, is typically done in the real world. So, while the z-test that we looked at in the last section for a population mean may be a good introduction to hypothesis testing, it unfortunately does not hold much use in the real world. And the reason for that is because most of the time when we're looking to test what the population mean might be, it's very rare that we're testing the population mean, but we know for absolute certain what the population standard deviation is. So it'd be kind of awkward that we have we know for a fact what the standard deviation of the population is, but we're still not sure of what the population mean is going to be. So, to alleviate that, a guy by the name of William Seeley Gossett, who under the pseudonym Student created a hypothesis test, which is known as the Student's t-test, for the population mean when the population standard deviation is unknown. The reason why it's not called Gossett's test is he worked for a company that allowed its employees to do research. Unfortunately, one of the employees before him gave away a lot of company trade secrets, so they decided that the employees could only do research using the company information if they didn't use the employee, if the employee didn't use their name, or they didn't mention what the company was about. So I'll let you look up William Seeley Gossett and see what company he worked for. So, all right. So assumptions for using the t-test for a population mean is that our sample comes from a normally distributed population, and this is especially important for small sample sizes. So for sample sizes that are less than 30. And that the sample is obtained randomly, so random sampling and simple random sampling. So with the student's t-test, it's going to be very similar to the z-test that we looked at before, but we're going to go back to what we talked about when we looked at the difference between population and standard deviation, and that is degrees of freedom. So recall that the degrees of freedom of a sample size, if the sample size is n, the degrees of freedom is given as n minus 1. So just take 1 away from the sample size and you have your degrees of freedom. So here we have some students' t-distribution graphs. So the red graph here is a degree of freedom of 1, and then right above it is a degree of freedom of 2, and then above that in orange is 5, and then in blue is 10. So it's very similar to our normal z distribution graph, but the shape of our student's t-distribution is affected by the sample size because it's affected by the degrees of freedom, which again, we just take 1 away from our sample size, and that's how we get these degrees of freedom. So as we can see, as the degrees of freedom grow, so red to green to orange to blue, as the degrees of freedom grow, the t-distribution is going to become more and more normal. So if we have a very large sample size, our t-distribution is going to resemble that normal distribution more precisely. So similar to a z-score, the t-test statistic can be found by calculating the difference between our sample mean and our claimed population mean divided by the standard error, which is the sample standard deviation divided by the square root of the sample size. Our p-value is still the area that's to the left of this t-statistic if it's a left-tailed test, to the right of this t-statistic if it's a right-tailed test, and outside of the positive and negative values of this t-statistic if it's a two-tailed test. So just like we talked about with the hypothesis testing for the z-test. Our confidence intervals very similar. The only real differences are, number one, with t-distributions, we are using our sample standard deviations because, again, we are not sure what the population standard deviation is. So the best we can do is use our sample. And then t sub alpha over 2, where instead of z sub alpha over 2. And again, the degrees of freedom, 1 less than the sample size, is going to help determine what this value is for our confidence intervals. Aside from that, everything else is pretty much just like it was with the hypothesis testing that we looked at with the z-tests. So You might be wondering, okay, this is getting kind of scary and uncharted territory with all this hypothesis testing. But truthfully, if you understood the ideas and concepts behind the hypothesis testing we've done, such as how we calculated our test statistic um, and compared it to our critical value, or how we calculated our p-value and looked at the significance level and compared it to the significance level, or with confidence intervals, if our confidence interval for our sample contained the population mean or not, then you should really be all right with this section. And matter of fact, you should be all right with just about all the hypothesis testing because they're all just going to be variations on that theme. We have these three different ways, and in a future video, we'll take a look at other ways as well to create these samples and make inferences about the population. But remember, most modern statistics use computers to crunch the numbers, so you don't have a whole lot of formula memorization in the way statistics is taught now. So let the computers and calculators do what they're good at. You need to be able to interpret those results, and that's really what the most important aspect of inferential statistics is. It's to be able to interpret the results that you get. All right, that about does it for this video. Thanks for watching. I'll see you next time.